Welcome back to Psych 1303, Statistical Methods. My name is Omar Carrasco, and today we're going to cover confidence intervals. This is part one, so we'll be talking about confidence intervals in our next lecture as well. But before we begin talking about confidence interval, let's review the main points from our last class. Last class we talked about the differences between three different kinds of distributions. So we talked about the sample distribution, the population distribution, and the sampling distribution. We mentioned that a sample distribution is a distribution of a variable in a particular sample. For instance, this graph shows the distribution in a sample from our Is Virginia example that we used last class. It shows that in a sample of 1,000 voters, 54% of them plan to vote for Christina Green. 46% of them do not plan to vote for Christina Green. On the bottom, we have our x-axis, and it's labeled as yes and no. However, we can rename these values, or we can assign actual numeric values to these yes and no values. So a yes response gets assigned a value of 1, a no response gets assigned a value of 0. So all we're doing is transforming the yes-no variable into a Bernoulli variable. The proportion of voters in the sample who are voting for green is 54%, or 0.54. In other words, P it's equal to 54% or 0.54, and because this is a Bernoulli variable, then the mean must also be equal to 0.54, or in other words, it's also equal to P. A population distribution is the distribution of a variable in the whole population. This graph shows the distribution of all 8 million voters in East Virginia. We can see that 55% of them plan to vote for green, and 45% of them do not plan to vote for green. So the population distribution and the sample distribution, when we compare them, they look very similar. So we have an x-axis with values yes and no. And we can do the same thing that we did with the sample distribution, and we can reassign these yes and no values a numeric value. So we assign a value of 1 for yes responses, and we assign a value of 0 for no responses. And something to note is that in a sample distribution and a population distribution, when we're talking about Bernoulli variables, there's only going to be 2 bars in the distribution, and that's because there's only 2 possible values in Bernoulli variables. So we only have 2 bars for this population distribution, and we had 2 bars for the sample distribution. So we know that the proportion of voters in the population who are voting for green is 55 or 55%. Or 0.55. That is, pi equals to 0.55 or 55%. So the population mean it's equal to pi, which is 0.55. So a sampling distribution looks a lot different from the previous 2 distributions. So it looks very different from the sample distribution and the population distribution. And the reason for that is because the sampling distribution is about the samples rather than the individuals. So when we were talking about the sample distribution showed that the proportion of individuals in a sample who plan to vote for Christina Green. The population distribution showed the proportion of individuals in the population who plan to vote for Christina Green. But the sampling distribution shows how many samples have a particular value of P. P being the proportion of voters in each sample who intend to vote for Christina Green. So we talked about the expected value of the sampling distribution of P. The expected value of P is simply the average of all values of P in the sampling distribution. For instance, if we have 700 samples and calculate P for each sample, we would have 700 values of P. If we average them, we get the expected value. Because the expected value is just an average, the expected value of P falls right in the middle of the sampling distribution. A very useful fact is that the expected value of P is always equal to pi, the mean of the population distribution. So here's the population distribution with the mean being equal to 0.55. And here's the sampling distributions whose average is the expected value of P. So the expected value of P, it's always going to be equal to pi, the mean of the population distribution. We also talked about the standard error of the sampling distribution of P. So the standard error is denoted as SE. The standard error is the standard deviation of all the values of P in the sampling distribution. So again, if you have 700 samples and calculate P for each sample, you have 700 values of P. If you calculate the standard deviation of these 700 values, you get the standard error. So the standard error is always going to be equal to sigma divided by the square root of n being the number of individuals in each sample. We also mentioned that the sampling distribution of P is normal if n is fairly large. But what do we consider fairly large? For practical purposes, we can say that if n is 30 or more, it's considered fairly large. So we also mentioned the central limit theorem and how it proves the sampling distribution is normal if n is fairly large. For this, all you have to remember is the name of the central limit theorem and what it proves. We also mentioned how to estimate the standard deviation from a histogram. To estimate the standard deviation, we first need to estimate the mean. So the mean is somewhere around this area. So we can say the mean is around about 34. And then we also need to estimate the 97.5 percentile score, which is somewhere around this end. So we can say it's about 52. Now, because 34 is at the mean, it has a C-score of 0. And because 52 is at the 97.5 percentile, it is equal to a C-score of 2. So the distance between 52 and 34 is 18. Or in other words, it's 2 standard deviations. So 18 is equal to 2 standard deviations. So when we divide 18 by 2, we get 9, which is equal to 1 standard deviation. And that tells us approximately the standard deviation of the population. Alright, so we're ready to cover the new topic for today. Today we're going to talk about confidence intervals. We need confidence intervals because P, which is the proportion in the sample, is almost always an imperfect estimator of pi, which is the proportion in the population. So remember that the whole purpose of statistics is trying to estimate or say something about a population. So we use samples, we gather data from samples in order to say something about the population. But because we cannot survey every single member in the population, we're going to have some error. We're going to have some imperfection. And confidence intervals provide some information about how well we're doing with estimates. So let's take this example. Let's say that Joanna Bolster conducts a poll in the state of East Virginia. Now, Joanna collects a sample of 1,000 voters and finds that 53% of them plan to vote for Christina Green. So the P equals to 0.53 for this sample. However, the value that she obtained for P is probably off as an estimate of pi, which is the proportion of voters in the whole state who plan to vote for Green. We call this imperfection a sampling error. Now, if she was to report her findings during the evening news, what should she say about the p-value that she found? One option is to pretend to be falsely confident about pi and say something like 53% of voters plan to vote for Green. However, this statement is misleading. It's a misleading claim of precision. Her second option is to be vague about pi and say something like about 53% of voters in the state plan to vote for Green. However, this fails to specify how precise the estimate is. Her third option is to provide an estimate, but then indicate how much it might be off. So she might say something like, my poll shows that 53% of voters plan to vote for Green, but the poll's margin of error is about 3%. So what does that mean? Well, we know that when she sampled the 1,000 voters, she found a p-value of 0.53. But the real question, or the question that she's trying to address, is the value in the population. So she's trying to find the value of pi. So we're trying to find the value of pi, and we know that the margin of error is about 3%. Given that her margin of error is 0.03, the pi value might actually be 0.56, which is 0.03 points away from 0.53. Or the pi value might actually be 0.50, which is 3% below 0.53. Or pi might actually be anywhere between 50 and 56. But she is 95% sure that pi lies somewhere on this line or interval between 50 and 56. In statistical terminology, we say that the 95% confidence interval of pi around p is 0.50 to 0.56. What this means is that the p of 0.53 is the best guess of pi. It's an imperfect guess, but we can be very nearly certain that the true value of pi lies somewhere between 0.50 and 0.56. That is, we can be almost certain that in the state, the proportion of voters who plan to vote for Green is no lower than 50 and no higher than 56%. On the graph, the confidence interval is indicated by a line segment between 2 points, 0.50 and 0.56. So your confidence interval is this bar right here. So we call this line segment the interval. And in math, the way of writing an interval is to write the two endpoints of the interval inside parentheses, the way shown on the screen. The left endpoint is the lower limit of the confidence interval, and the right endpoint is the upper limit of the confidence interval, or upper boundary. Now, the example that we just covered talks about how to find the confidence interval for pi around p. But first, we need to understand the confidence interval for p around pi in order to understand or fully comprehend the confidence interval for pi around p. So we're going to cover an example of estimating the 95% confidence interval for p around pi. So we're going to use the same example that we've used in the last couple of classes, where we're looking at West Virginia voters and how they plan to vote with 700 groups, each group containing 1,000 individuals. So here we have the sampling distribution, and we can see this is the sampling distribution for the 700 samples, each with 1,000 voters. Okay, so there's 700 samples making up this sampling distribution. On the x-axis, we have the proportion who intend to vote for green, or the p-values, in other words. And then on the y-axis is the number of samples that have a certain p-value. So for example, we can look at the p-value of between 0.59 and 0.50, just this bar right here, and we can see that not many samples had a value of 0.50. However, if we look at an example of 0.55, we see that a lot of the samples, almost a little bit over 80, had a value of 0.55. Now remember that in a normal distribution, the mean is always going to live right at the center. Well, if we're talking about the mean of this 700 samples, or the expected value of p, in other words, we know that the value is going to be right at the center. That's the value of pi as well. So remember that pi, it's always going to be equal to the expected value of p. So we can estimate the two standard deviations above, or two standard errors above the mean, which is around this area. And we can also estimate two standard errors below the mean, which is around this area. So this area right here indicates all the p-values that fall within two standard errors from pi, or the expected value of p. So what percent of the samples fall within two standard errors from the expected value of p, or from pi? Well, this is something we covered at the beginning of the semester. So if you remember, there was how much area is covered within one standard deviation, how much area is covered within two standard deviations. It's the same concept that we apply here. In a normal distribution, 95% of the scores lie within two standard deviations of the mean. Now, the sampling distribution of p is normal if n is greater than 30, which in this case we had an m value of 1,000. So we have enough individuals in our samples. So again, what percent of the samples have a p-value within two standard errors from pi? Well, in a sampling distribution of p, 95% of samples have p within 2 standard errors of the expected value, or from pi. So 95% of samples fall within this rectangle, or 2 standard errors below or above the mean, or pi. So this line at the bottom indicates the 95% confidence interval of p around the expected value, or around pi. That is, if the expected value and pi are 0.55, and we select any single sample at random from this entire distribution, then 95% of the time the value of p for the sample will be on this interval, or in our confidence interval. So we can write this as the 95% confidence interval for p, which is equal to 0.52 and 0.58. Remember, 0.52 is the lower level, the lower boundary, and 0.58 is the upper boundary. In other words, 95% of samples have a p-value between 0.52 and 0.58. We can also state this as a margin of error of about 3%. Given that pi is 55, we have about a 3% margin of error. So just by looking at the histogram of the sampling distribution, we can estimate the 95% confidence interval for p around pi. So the lower limit of the 95% confidence interval is 0.52. The upper limit of the 95% confidence interval is 0.58. So here are the values. And we can write them as p lower equals to 0.52 and p upper equals to 0.58. Now, so far, we've only been estimating the confidence interval for p. So we looked at the histogram. We kind of gauge where the 2 standard errors below the mean and 2 standard errors above the mean were located. And from there, we built a confidence interval. But that's just an estimate. Now we're going to cover an example of calculating the exact 95% confidence interval for p around pi. So we're going to use the same example, but now we're going to do a precise confidence interval. And in order to have a precise confidence interval, we need 3 things. So we need the expected value of p, we need the standard error, and we need the value of n. So what is the expected value of p? Well, the expected value of p, we know it's always going to be equal to pi. In other words, the proportion of individuals who plan to vote for green. So what's the value of pi? Well, for this example, we've been mentioning that the value of pi is 0.55. In real life scenarios, you're not going to know the value of pi. The reason for that is, well, you rarely have access to every single member in the population. So you're not going to be able to collect data from every single member in the population. So that means that even if you miss just one person from the population, you don't have the information about the population. You actually have the sample information. So you rarely have opportunity to collect data from the entire population. So for this example, let's assume that we obtain the information about pi from the recording angel in charge of voting and opinions. So this angel told us the actual value of pi. So the actual value of pi that was given to us by the angel was 0.55. So what is the standard error? Well, the standard error is equal to sigma, or the standard deviation, divided by the square root of n. Sigma is the standard deviation of the population. So we know that pi is equal to 0.55. And we're going to use pi in order to calculate the standard deviation. Remember that the standard deviation for p is equal to the square root of p times q. So in order to calculate the standard deviation of the population, we're going to use the square root of pi times q. When we were talking about p-values, q was calculating by subtracting 1 minus p. So this time, in order to calculate the population standard deviation, we're going to subtract 1 minus pi. So essentially what we have is the standard deviation of the population is equal to the square root of pi times q. So we know that the value of the population, or pi, is equal to 0.55. And all we have to do is find the value of q, which is in this case is 0.45. And we end up with a standard deviation of 0.497. So now all we have to do is calculate our standard deviation into our formula in order to calculate the standard error. So the standard error is going to equal to 0.497 divided by the square root of n. Well, what's the value of n? Well, n is the number of individuals per sample. And in this scenario, or this example, we had 1,000 individuals. So we end up with a standard error of 0.016. So we mentioned earlier that for a precise confidence interval, we need to know the expected value of p, the standard error, and n. Well, we have those values already. So expected value of p is 0.55, the standard error is 0.016, and n is equal to 1,000. So in order to calculate the upper limit, we need to use this formula. Now, what is this formula telling you? Well, the formula is telling you that you need to find the value of 2 standard errors and add that value to the expected value of p. So basically, you're adding 2 standard errors to the expected value of p in order to find the upper limit. So you take the value of, or the expected value of p, and you're finding the value 2 standard deviation or 2 standard errors above the expected value of p. So we plug in our values, 0.55 and 0.016, and we end up with an upper limit of 0.582. When we estimated the upper limit of the 95% confidence interval, we came up with a value of 0.58. We came up with an estimate of 0.58. So when we compare this to the actual value, it's not that off. We were very close to the actual value. So the lower limit formula is going to be very similar. However, we are now looking for the value 2 standard errors below the expected value of p. So now instead of adding, we're subtracting from the expected value. We're subtracting 2 standard errors. So essentially what we're finding is the value at 2 standard errors below the expected value of p. So we take our formula and plug in our values, and we find that the lower limit is 0.518. When we estimated the lower limit, we found that the lower limit was close to 0.52, so we're not that off. We weren't that off compared to the actual value. So the precise 95% confidence interval is between 0.518 and 0.582. So this tells us that if 0.55 of the population, or 55% of the population, plan to vote for green, and the pollsters conduct surveys of 1,000 people, we can expect those samples to fall between 0.518 and 0.582 95% of the time. Okay, let's review what we discovered. So to find the 95% confidence interval for P, you're going to need the expected value of P, you're going to need the standard error, and you're going to need the value of N. Then you're going to need to find the upper limit by adding 2 standard errors to the expected value of P. And then you need to find the lower limit by subtracting 2 standard errors from the expected value of P. So the value, or the expected value of P, must be given to you. Okay, so for quizzes, for exams, we're going to give you the value of pi. We're not going to tell you pi is equal to blah blah blah. We're going to phrase it differently. We're going to tell you, for example, 0.58% of the population plan to vote for green. So then you have to understand that when we talk about population, we are talking about pi. Then the standard error can be calculated using these 2 formulas. So first you need to find the standard deviation of the population. So once you know the value of pi, you're gonna multiply that times q, and then find the square root. Find the square root of the value that you obtain. Once you find the standard deviation, then you're gonna plug in the standard deviation into this formula in order to find the standard error. Okay, so let's do a class exercise. So we know that Ireland is 84% Catholic. We conduct 1,000 surveys asking people whether they were Catholic or not. Each survey contained 100 individuals. Now your job is to find the 95% confidence interval of P. P being the proportion of individuals reporting being Catholic in the surveys. So take a few minutes to answer this question, and then come back for the answer. So try to do it by yourself and then come back. Okay, in order to find the 95% confidence interval for P, we need the expected value of P, we need the standard error of our sampling distribution, and we need N, or the number of individuals in each survey. Okay, so this is the information that we gave you. Okay, we said that Ireland is 84% Catholic. We conduct 1,000 surveys. Each survey contains 100 individuals, and P is basically the percent of Catholics in each sample, or the percent of individuals who identify themselves as Catholics. Okay. So what's the expected value of P from the information that we gave you? Well, the expected value of P, it's equal to the population value. And we know that the population of Ireland, it's 84% Catholic. So the expected value of P is equal to pi, which pi in this scenario is 0.84. What about N? Well, N is the number of individuals in each sample. And we mentioned that each sample contained 100 individuals. So N is equal to 100. Okay, now we need the standard deviation of the population. So the standard deviation of the population can be calculated by finding the square root of pi times q. So we know that pi is 0.84, and we already know how to calculate q. So in this case, to calculate q, we subtract 1 minus pi. So we end up with a value of 0.16. So we find the square root of 0.84 times 0.16, and we end up with a value of 0.367. So the standard deviation of the population is 0.367. So now we need to calculate the standard error. So the standard error, remember, it's equal to sigma divided by the square root of n. So when we plug in our values, we carry out our calculations, and we end up with a standard error of 0.0367. Alright, now we have to find the upper limit and the lower limit of the 95% confidence interval. So in order to find the upper limit of the 95% confidence interval, we need to multiply our standard error times 2 and then add that value to the expected value of P. So we multiply 2 times the standard error and then add it to the expected value of P. In order to find the lower limit, we need to multiply 2 standard errors, but then subtract 2 standard errors from the expected value of P. So our upper limit is going to be equal to 0.913. Our lower limit is going to be equal to 0.767. Okay, our 95% confidence interval is between 0.767 and 0.913. So if we were to take another survey from this population and we ended up with a p-value of 50%, so let's say that 50% of individuals reported being Catholic, what would you say about this survey? Well, would you say that the survey was conducted correctly and everyone was randomly sampled, or it contained a random sample? Or would you say that something was wrong and that the value is probably very unlikely to be a value that represents the population, knowing your 95% confidence interval? Well, you would say that it's highly unlikely because 0.50 doesn't fall anywhere close to our 95% confidence interval. It's a very, very unlikely value to happen. Alright, so we know how to find the 95% confidence interval for P around pi. But what do we want to find a 99.7% confidence interval for P around pi? We can use the same method, and the only thing that's going to change is the last 2 steps. So in the last 2 steps, we multiply 2 times the standard error in order to find our upper limit and our lower limit, because 95% of the data falls within 2 standard errors. Well, remember at the beginning of the semester, we gave you 3 different values to remember: 68%, 95, and 99.7%. So 99.7% of the data is going to fall within 3 standard deviations from the mean. So in order to calculate a 99.7% confidence interval, instead of multiplying times 2, we're going to multiply by a different value. And that value is going to be 3. Because 99.7% of the data falls within 3 standard errors. We can do the same thing for a 68% confidence interval, but instead of multiplying times 3 or by 2, we would multiply by 1. Okay, so we're almost done with the lecture, but before we end, let's summarize what we learned so far. So we talked about confidence intervals, and basically confidence intervals provide a margin of error for your statistics. So confidence intervals are more informative than just calculating a p-value. We talked about how to calculate the confidence interval. So we talked about how to calculate the confidence interval for p around pi. So we know the value of pi, and we're trying to find the likely values of p. Okay, so in order to find the 95% confidence interval of pi, of p from pi, we need to know the value of pi. So you find out the value of pi. You need to know how many individuals were in each survey, and then from there you calculate the confidence interval. So you need the standard error, the expected value of p, which is going to be pi, basically, and then you need how many individuals were in each survey. Okay, so that's the end of the lecture. Next class, we're going to continue with confidence intervals part 2. There's going to be homeworks assigned for the next lecture, and there's going to be a quiz. So make sure that you guys are starting to read early and doing your homeworks. Confidence intervals, it's one of the most confusing topics of this class. So please take your time in completing those. I hope you guys have a great week, and we'll see you next time.